Okay, so in this video, we're going to talk about how we can actually quantify work based upon a reaction. Now, I have an example reaction here where we have hydrogen, oxygen producing water. Now, if we were going to calculate work, right, we said we're dealing with this idea of expansion work, and so work is equal to the negative of the pressure times the change in volume. Now, if you remember, work is a measurement of energy, right, or expelled energy. Well, if we think about pressure and volume multiplied divided together, how would that give us something dealing with energy? Okay, so let's go ahead and think about when this reaction happens, or a reaction happens, what is going to be the thing that causes expansion or contraction to happen at constant pressure? Well, if we're thinking about the different physical states we can have, solid, liquid, or gas. Well, if we take 1 mole of solid, produce another mole of solid, the volume, maybe 2 moles of solid, that's not going to really change the amount, right? The volume that much. Or if we think about liquid, we talk about liquids changing and reacting. The volume's not going to expand or contract very much if we go from, like this say was 2 moles of a liquid to 1 mole of a liquid to 2 moles of a liquid. It's not going to change that much. But if we're thinking about a gas, if you go back to the ideal gas law, PV equals nRT, well, if you're at constant pressure and you double the number of moles, that's going to double your volume, okay? And so that we see that what's going to cause the greatest amount of change in volume? Number of moles of gas, right? Our gas molecules. That's what's going to cause our volume to change drastically compared to maybe a liquid or solid, okay? So we're going to go and unpack this with regards to the ideal gas law, okay? So we want to look at the relationship between volume, number of moles. Okay, so I'm going to kind of separate out this RT over V, because if we're doing this, RT over P, if we're doing this at constant pressure, our pressure is going to be constant, our temperature is remaining fairly constant, and R is the gas constant. It doesn't change, it's a constant value. So the only way that our volume can really change is by changing the number of moles. So now if we want to look at a change in number of moles, we can look our change in volume. We say our change in volume equals the change in number of moles times RT over P. Okay, well, let's go ahead and let's plug that in here into that relationship. So now we have work equals negative pressure, and I'm going to put this expression in here. Change in number of moles times R times T over P. So now we see our pressure gets canceled out, and we end up with work equals negative change in number of moles. Okay, now to be explicit so that we make sure we remember, what is this the change in number of moles of? It's the change in the number of moles of our gas molecules, right? Because ideal gas law only applies to gases, okay? And then that would be times R times T, okay? So we go back to our R value. We're going to use a different R value than we used previously because now we're dealing with energy, okay? Same idea of converting between different units. We just have different units of our R value. So it's going to be joules per mole per Kelvin, okay? And so what does that mean? Our temperature needs to be in, well, be in units of Kelvin, okay? So now going back to this reaction, can we actually quantify how much work may be done by or on our system, our reaction? Well, we have a reaction here. Let's go ahead and say that this was done at 25 degrees Celsius, or we could say add 273, 298 Kelvin. Okay, so now we know the temperature that it's occurring at. R is a constant. We need to calculate the work. Well, we can say our work is equal to negative the change in number of moles of gas. Okay, so that would be products minus reactants. Well, this is a liquid. So that would mean we have 0 moles of gas as a product, right? Those 2 moles are a liquid. Here we have 1 plus another 2 moles of gas as a reactant. Okay, and then we multiply that by our gas constant, 8.314 joules per mole Kelvin. And then we can go ahead and multiply that by our temperature, 298 Kelvin. We go back and we see our units cancel out here, our moles cancel out here, and we could go ahead and calculate what the work would be, and this is equal to 7,430, our units here, joules, okay, or we could say it's 7.43, not 43 kilojoules. So now we see we can actually quantify work. And what we're going to see in class is we're going to look at the fact that we can compare now internal energy and enthalpy and see how those two things are related to each other with regards to this idea of work. So I'll see you in class.